All right, so I'm going to start off by choosing my u to be the inside of that radical. And then that's going to give me a du of 2x dx. And so when I look at this, that's not really helpful, but every other u I've tried hasn't been helpful either. So I'm going to go ahead and fill in my u. And then I want to get rid of my x to the fifth dx. The problem is that I don't have an x to the fifth dx. So instead, what I did was I just solved for dx first, got rid of that. So if I solve for dx, I would divide that. Okay, so now I've got dx that I can fill in. And then if I simplify that down a little bit, I've got square root u, and then these x's will reduce, and I've got a 2 on the bottom. So I'm going to write that as 1/2 x to the fourth du. And then I still have this x to the fourth that I have to get rid of. And so what I looked at was my u up here. And I figured I can change x squared to x to the fourth. So let's look at that. First of all, I want x to the fourth. So I isolated my x squared. So I subtracted 1 to the other side. And then to get x to the fourth, I'm going to square both sides. And now I can substitute in my x to the fourth. And that's going to be u minus 1 squared, and then I've got du. So it doesn't look like I've simplified it very much, but this is going to be helpful. If I bring my 1/2 in front and get rid of that, and change this u to 1/2, and if I go ahead and square u minus 1, I can find the integration here if I FOIL like I did and distribute. So we're adding exponents here, so that's going to be 5/2 and 3/2. Okay. And then, so I've simplified it. This is as simple as I can get it, and now I'm going to do the antiderivative. So we're adding 1 to the exponents and then dividing. So if I add 2/2 to these, I end up getting u to the 7/2, and so then you multiply by the reciprocal. I'll have u to the 5/2 and multiply by the reciprocal. And I'll have u to the 3/2 multiply by the reciprocal. And then I've got plus c. And if I distribute my 1/2, that will give me 1/7. That'll give me 2/5 and 1/3. So that is my integration with u, and then I need to fill u back in. And that is your answer. In example 6, tangent looks simplified, but we don't have any derivatives that give us tangent. We know that tangent's derivative is secant squared, but here when we're going backwards, we need to have secant squared. We can't have tangent. So we don't have a known antiderivative for tangent. So what we're going to do is change it into sine over cosine. And then we want to decide where to put the U substitution. Um, so one thing would be to make sine your U, and then cosine would be, um, well, let me just do it, but this isn't going to work. Okay, so what I would have here is U on top, but then I need to have cosine on the bottom, and here cosine's on the top with dx. So it just doesn't work really that easily. So instead, I decided to let U equal the bottom. And then that way my du is on top where, so sine x dx is on top where it belongs. So if I fill in my u, I've got sine x dx over u. And then I want to get rid of sine x dx. So if I move that negative over, then I can fill in sine x dx with negative du. And let's move that negative in front and look at this as 1 over u du. And so if we do the antiderivative of that, we end up getting negative natural log of absolute value u plus c. And then we plug in our u, which is cosine x. And so that would be your antiderivative.